So here's what we're going to do. We essentially want to calculate this quotient, right? Okay, that's cool. Now, what do we do? Well, if this 5 were not here, we can use synthetic division, right? I can get the 5 out of there, though. Basically, I can divide top and bottom by 5, which algebraically is the same as multiplying by a fifth, which is what I'm doing. I mean, I could just dive right in and divide by 5 directly. That's essentially, after this, that's essentially what I'm doing here, right? I'm dividing top and bottom by 5. Right, and how does that help us? Well, on the bottom, the 5s are going to cancel. We get x plus 3 over 5. For the top, though, what I did remember was I distribute, like so, and we get this. 25 over 5, that's 5 x cubed. 150 over 5 is 30 squared. 131 over 5 is just 131 over 5. I mean, you probably could actually divide it in a calculator, I guess, but let's leave it like this. 30 over 5 is 6. I don't think it's a nice decimal, so I mean, theoretically, you could write it out as a decimal, but sometimes you may have to round. So let's keep it as a fraction. All right. So that was fun. But now we can apply synthetic division. Namely, we can do this. Right? Because now we have x plus a number. So now we can use synthetic division. So we're basically using it on this polynomial, which I'm calling g. Okay, so let's do that. Notice it's already in standard form, meaning it's listed, so that as you read it from left to right, the powers of x are going down. We have x plus, x, we want it as x minus something. We have x plus 3/5. So what do? Write it as x minus negative 3/5, like so. So with synthetic division, okay, we just have negative 3/5 here. Coefficients, we list. Notice also that there are no missing powers of x, right? You go from the degree, which is 3, down to the constant term, the last term, and all the powers of x are here, the, I guess, intermediate powers, so to say. So we don't have to use 0 as a placeholder. The coefficients in the constant term, we list. All right. So what do we do next? This 5 comes down. Negative 3 over 5. Here, let me draw it out. Nope, wrong one. Perfect. So we multiply like so. When you multiply negative 3 over 5 times 5, the 5s cancel. You're left with negative 3. And here, the 30. Then here, 30 plus negative 3, right? You add, and you get 27. Then you basically do the same thing. Now you're going to work on 27. So we have negative 3 over 5 times 27. We end up with this. Now, if you multiply, remember, you get negative 81 over 5. You're multiplying 3 by 27. When you add and subtract fractions, you have to keep the denominator as the same. You need a common denominator, which we have here. So we have 131 over 5 plus negative 81 over 5, which is 50 over 5, which is 10. Minus 3 over 5 times 10, that's minus 30 over 5, which is minus 6. And so 6 plus minus 6, we get a 0. So altogether, this is the same chart from before. Altogether, then, what's our quotient? Well, Since this was degree 3, our quotient will be degree 2. We'll have 5x squared plus 27x plus 10. 0, that's our remainder. This number is our remainder. And here, this is just from the division algorithm. What do we get? Well, this is our original polynomial, which was this. We're dividing by d. This is our wonderful d. This is our quotient we just calculated. Here's our remainder. And 0 over anything is 0. So we really just have this. Now, if you remember, though, we divided top and bottom by 5. Same thing as multiplying by a fifth. But really, we want to be back in the original situation, so we put the 5 back by multiplying top and bottom. Right? To get to this, before synthetic division, I guess, we had to divide top and bottom by 5. Here, I'm multiplying by 5, top and bottom. Now, this is what we had, what we started with. So now we're good. So we end up with this. All right, that's good. Mostly because we want 5x plus 3 here. That's really why we multiplied and divided by 5. So that's what we get. And I guess if we wanted to keep going, we could theoretically factor this here, although I don't want to do that. So it looks kind of nasty. Well, it's not terrible, I think, but let's not do it for now. Okay, so I know it looks kind of crazy, the calculations we did, but this is essentially what we did. If you're taking a polynomial and you're dividing it by this, we're assuming a is not 0. And I guess in a sense, we're assuming b is not 0. Because if b were 0, you wouldn't have to do synthetic division. So basically, we're dividing f of x by a. You do synthetic division here. And when we do that, this is what we're going to end up with. And then, since this is an equation, and we want f of x here, and we want ax minus b, we have to multiply both sides by a. So we essentially divided both sides. We essentially divided these by a, then we multiply by a to get back to the original problem. And yes, we get a times the remainder. I mean, yeah, that's in theory, but that's not really going to affect us too much. So basically, we're just dividing by a, then we're multiplying by a. I mean, the calculation's illustrating why we can do that and the idea behind this procedure. What's nice about this also is you can actually get a factor theorem and a remainder theorem for this case. Mostly because the degree of this thing is 1. And so what you actually get is the remainder, a times r of x, turns out to be this. It's really the same steps as we did for the remainder theorem the first time, for the first remainder theorem. And really what made it work was the degree of this is 1. So, but if you went through those steps, or something similar, I should say, this whole remainder term would be this, capital F of b over a. In other words, we're going to end up with this, is what I'm saying. When the dust settles and you dive in and do all that stuff, you end up with this, as you can see. And in particular from here, what happens is this. We get that ax minus b is a factor of capital F exactly when, or if and only if, this thing is 0. This thing is 0, if and only if. So it's a sort of remainder and factor theorem for this case. Okay. I thought it'd be good to throw that out at you. So, okay, that's fun. Any questions at all? I figured you'd do some examples now. You can see the stuff in action. Okay. So let's do another example. So we're going to take this polynomial, we're going to divide it by 3x minus 5. Again, this is not x minus something, it's 3x minus something. So we have to divide by 3. Now, before we do that, I can actually figure out using this what the remainder is. And that's what I'm doing. I'm just calculating this f at 5 over 3, right? Here we had ax minus b, b over a. So I'm doing this at 5 over 3. And this tells us this will be the remainder if we divide this here by this. So in particular, this is not a factor of this. That's okay. Okay, that's great. Now, to actually divide and use synthetic division, as you can see, we divided by 3, both f and both the dividend and the divisor, as you can see. So we're going to use synthetic division here. Okay. Let me stop the clock first. Well, let me stop the recording first.